As with most of our class notes, I just want to emphasize again that these are all problems that you should try to do before I show you the solution to them. So, for this first one and all of them, just kind of pause the video and give it a try yourself. We're going to be both proving identities and kind of more focused on these new identities we've learned, the addition, subtraction, double angle identities. And then also we will be solving some equations in this too. All right, so in example 1 here, it asks us to prove that the sine of pi over 2 minus x is equal to the cosine of x. All right, so the left-hand side is certainly more complicated, I think, than the right-hand side. So let's start with it. Now what we have are two different angles being subtracted. So this is the subtraction formula for sine, and so that's sine, cosine, cosine, sine. And then remember with sine, whatever symbol's in here is the same symbol that's going to be out there. All right, but of course the sine of pi over 2 is 1, right? But then the cosine of pi over 2 is 0. So that, of course, goes away. We're left with the cosine of x, which is, of course, our right-hand side. Right, and so you can see that the sine and cosine, have this relationship where, you can get just flip and then shift the sine over, and then you've got the cosine graph. All right, so let's take a look at example 2. So we want to prove this identity. I think the left side of that thing is much more complicated than the right side, so let's start with it. So the sine of a plus b plus the sine of a minus b. But just like in that last problem, we've got addition and subtraction formulas here. So this one turns into, right, remember, sine, cosine, plus cosine, sine. That's all just this one. And then the other one here is plus sine, cosine, minus cosine, sine. But if you take a look here, cosine A times sine B appears here, and then the negative of it appears here, so those just go away. And then sine A cosine B appears twice, so that's 2 times the sine A times the cosine of B. And that is our right-hand side, so we've proved that one as well. All right, so here's another one that they're asking us to prove, and again, the left-hand side of this thing definitely seems more complex than the right-hand side, so let's start with that. But now let's think ahead a little bit. We're trying to create a tangent on the right side. So we know that tangent is sine divided by cosine. So with the double angle formula for cosine, we have options, right? We can say that it's equal to the cosine squared of theta minus the sine squared of theta. We can say that it's 2 cosine squared theta minus 1. And we can say that it's 1 minus 2 sine squared theta. So we have 3 different versions of the double angle formula for cosine. Now, my thinking here is that this one's the best choice because I know that tangent's got a sine on top, so I'm going to pick the one that just has sines in it. So I'm going to take 1 minus, and then I'm going to replace the cosine of 2 theta with this. But remember, be careful when you do that. You are going to subtract from here, you're going to subtract that entire thing, so make sure you put it in parentheses. And then on the bottom, sine of 2 theta, there's only one version of that, right? So we got no choice in the matter there. 2 sine theta cosine theta. So we'll write that out. All right, but then when we distribute this 1 through, we end up with 1 minus 1 plus 2 sine squared theta, all divided by 2 sine theta cosine theta. And then 1 minus 1, of course, becomes 0. But then the nice thing here is that, we got too many signs on top. We don't want signs on bottom. But we get some cancellation that has everything we need to happen. So the 2's go away. One of the signs go away on the top. And so we're left with sine theta cosine theta over cosine theta, which of course is the tangent of theta, which is our right-hand side. All right, so let's take a look at example 4 here. All right, so this one, I could see maybe starting with either side, but here's what I'm thinking. The left side's more appealing to me because if I see like a minus b, then that tells me I can expand it out with the subtraction formula for sine, and I like the idea of being able to expand it out on the left, and then maybe doing some canceling to get what we have on the right. So I'm going to go ahead and again choose the left-hand side as my starting place. So again, remember the rhyme: sine, cosine, cosine, sine. And then it's over cosine of A, cosine of B. All right. Now, in a situation where you have two different terms on top and just one on bottom, you can always separate that out. And on the right-hand side, we can see we have two distinct terms subtracted. So we can certainly say it's this first term over the cosine of A, cosine of B, minus cosine of A, sine of B, over cosine of A, cosine of B. And then, of course, some nice cancellation happens that really does the job for us, right? Cosine of B's cancel, cosine of A's cancel. And we've just got sine over cosine in both terms. So that's the tangent of A minus the tangent of B, which of course is our right-hand side. All right, let's do one more proof problem here. So we have the 2 times the cosecant of 2x is equal to the tangent of x plus the cotangent of x. Okay. So this one, I think I could see doing this in a couple of different ways. And you might look at the cosecant of 2x and say, well, okay, what's that, Cosecant of 2x, all right? But let's, this might be one that might be good to work on both at the same time. So, that 2 cosecant of 2x, that's our left-hand side, right? What is that? Well, remember cosecant is 1 over the sine, so this is 2 over the sine of 2x. And whenever I see that, I know that I can expand that out to 2 sine x cosine x, and then of course those 2's can cancel out. So this is 1 over the sine of x times the cosine of x. Now at this point, I'm really not sure how that gets me here, okay? So remember, it's okay to work on the sides simultaneously, or work on the sides separately, and if you can show that they both end up equaling the same thing, then you're in good shape. So let's investigate the right-hand side. Maybe we can make it look like this. So the tangent of x plus the cotangent of x is equal to sine of x over the cosine of x plus the cosine of x over the sine of x. And then we can multiply the top and bottom in order to make a common denominator in both of these. And that's good because that denominator we're creating, that is what we have on the bottom of this, of when we work the other side out. So this is going to be sine squared x plus cosine squared x, all divided by sine x cosine x. But that's great news because it's our old friend sine squared plus cosine squared. So here's a good example of one where we were able to work on both sides until we could show that they were actually equal to the same thing. So that proves that the left-hand side and the right-hand side are in fact equal. All right, so let's look at example 6 here. It's asking us to find the cosine of 2 beta if the sine of beta, or sorry, cosine of 2b, excuse me, if the sine of b is 0.6 and b is in quadrant 2. All right. So if we want to know the cosine of 2b, and all we know right now is the sine, similarly to the discussion we had before, we have options. Right? We could say this, but then that would require me to figure out what the cosine of b is, which I could do. But then we also have one that involves only sine. So in the interest of being a little bit lazier, how about we just use this one? Because we know the sine of b. So this could be 1 minus 2 sine squared b, which is 1 minus 2 times 0.6 squared, 1 minus 2 times 0.36. So it looks like we get 0.28. Now, just make sure we're careful here. It says b is in quadrant 2, but we're finding the cosine of 2b. So you might be thinking, well, cosine should be negative there. Well, yeah, cosine of b is negative in quadrant 2. Cosine of 2b is not necessarily in quadrant 2. And, just to maybe illustrate this in a quick picture of the unit circle, if b is in quadrant 2, maybe it's right here. If you double b, it's conceivable that ends up over in the quadrant 4 where cosine is positive. So that's why we're getting a positive answer there. All right, let's look at example 7, right? We're being asked to find the cosine of 15 degrees, and we want the exact value, right? So no fair picking up the calculator at this point. All right, so we've done a couple, maybe 1 or 2 of these before, I think in the video notes. So cosine of 15 degrees. So remember what we're going to try to do is we're going to try to write 15 degrees in a way that a special value shows up. And I think this would be instructive to maybe do a couple of different ways. So for one, the cosine of 15 degrees could be the cosine of 45 degrees minus 30 degrees. We could do that, which is cosine plus sine root 2 over 2, root 3 over 2, plus root 2 over 2, 1/2. So that's square root of 6 plus the square root of 2 all over 4. Okay. Now there wasn't anything special about 45 degrees and 30 degrees other than the fact that they subtract to make 15. So, you know, if you wanted to here, you could also say something like this, right? Cosine of 15. Well, that could also be the cosine of 60 degrees minus 45 degrees. And you have different numbers involved, but cosine of 60 degrees, cosine of 45 degrees plus the sine of 60 and the sine of 45. That's still going to yield the same answer, right? Because the cosine of 60 degrees is 1/2. Cosine of 45 is root 2 over 2. And then the square root of 3 over 2 for the sine of 60, and then root 2 over 2 for the sine of 45. So get the exact same answer here, of course. Right? Just switch the order of the addition. Right? So you're not necessarily tied down to just one way of looking at it. You just want to try to make 15 degrees with some sort of special values. All right, so now let's look at example 8. Let's solve this equation here. Now, normally, understand, we're not afraid to solve an equation that has something more complicated in the argument. We did that a lot back in Standard 12. But that would be things like this, right? The sine of 2x is equal to negative 1/2. So that's no problem. But it is a problem when you've got 2x in the argument of one and then x in an argument of another trig function. So what we definitely want to do is have everything on the same page. So I know that I can easily turn this into just having trig functions of x if I go ahead and use the double angle formula for sine. And then in a scenario like this, right, resist the urge to divide by sine. That's going to lose solutions for you. Rather, subtract and set it equal to 0. So I have 2 sine x cosine x minus the sine of x is equal to 0. And then we've seen problems like this before, right? We can see that we can factor a sine out of both terms, and we're left with 2 cosine x minus 1 is equal to 0. So on the one hand, we get the sine of x equals 0, and we know that that's going to happen anytime x is equal to k pi, right? Because on our unit circle, sine equals 0 here, and it equals 0 here, so every multiple of pi. All right, here there's a little more going on. All right, we need to get the cosine all by itself. Okay, but we note that the cosine will equal 1/2 in quadrant 1 and quadrant 4. So it looks like that's going to happen when x is equal to pi over 3 plus 2k pi, or x equals 5 pi over 3, or you could write negative pi over 3 there as well, doesn't matter, plus 2k pi. All right, and I'll just add my other one right here, x equals k pi, so that we have them all written together there. All right, now for this last one, we're going to break the rules a little bit. We're being asked to prove that the left equals the right, and I think there's no question that the right side of this is more complicated. However, kind of the exception to that rule is that if you see one of your formulas that you've learned showing up on one side, it might be nice to start with that and then expand it out. So I'm going to go ahead and start with the left-hand side because I know that that's that half angle formula we were talking about. So this is going to be 1 plus the cosine of theta all divided by 2. All right. So from there, you might say, well, that doesn't look a whole lot like what we've got here. But notice what we have. We've got tangents on both the top and bottom. Then we have a sine here. So remember, this is where we don't try to do too much at once. All we say is, okay, I need tangents to appear, so let's make tangents appear. Let's just do it legally. So I'm going to take what I already have, and then I'm going to multiply on the top and bottom by the tangent of theta. So we have the tangent of theta when I distribute through. And that's good. That's what we want right there. Plus the cosine of theta, tangent of theta, all divided by 2. Oops. Let's fix this up a little bit. All divided by 2 tangent of theta. So we got almost everything we want here. And remember, if you're ever unsure about your next step, right, maybe write things out in terms of sines and cosines. I'm going to leave these alone because that's exactly what I want to show up. But in this term here, let's write that out as sines and cosines. So this is plus cosine theta, and then instead of tangent, we'll say sine theta over the cosine of theta. And that's all being divided by 2 tangent of theta. But then you can see exactly what we want to happen has happened. Those cosines cancel, and I'm left with this sine that I have in that term. So to clean this up, this is just the tangent of theta plus the sine of theta divided by 2 tangent theta, which is our right-hand side.